So today we're going to talk about waves. What are waves? Well, there are transverse and longitudinal waves. One thing you need to know is that all waves travel through a medium. The main difference between transverse and longitudinal waves is that the disturbance is perpendicular to the direction of the wave for transverse. Disturbance is in the same direction as the longitudinal wave travels. So, what are the wavelengths between a transverse and longitudinal wave? Well, for transverse waves, the wavelength is from trough to trough, crest to crest, or from the middle to the middle. And for longitudinal waves, it's from where it's compressed to another spot where it's compressed, or where it's both spread out. But waves don't always look like this. Sometimes they can look like a pulse, which is just one disturbance through the medium. The other type of wave is a standing wave. It's often seen with guitar strings, where the wavelength is like this. You can figure this out because in a normal transverse wave, it's from the middle to the middle. So if we complete this into like an infinity sign, then it looks like this standing wave wavelength, which matches. These are the nodes. They're the points where it seems like the two strings, which is really one just vibrating, come together, and the very top where it moves the most is the antinode. The nodes are usually fixed points that don't move. Now, the number of waves that pass a point in a given time is called the frequency. The frequency can be shown with the equation F equals n over t. The unit for frequency is hertz, which is really something per second. The time it takes for one wavelength to pass a certain point is called the period. This sentence can be shown easily in an equation T equals T over n, big T meaning period. This is just in seconds because it's seconds over a number. You can notice that this is the inverse from the frequency equation, so we can also write frequency as 1 over t or period as 1 over frequency. One way to visualize this is if you're on a boat. Say you're at the top of a wave and then the wave is moving beneath you. The time it takes for you to go down and up to the next wave is the period. Now let's do an example. So, in the first example, the time is 1, second time is 2, and the third time is 3. So let's use the first one because it has the easiest numbers. T is 1 and n is 2. When we plug this in, the period equals half a second. So the period of this wave is half a second. Now what about standing waves? We brought this up earlier, but let's go into further detail. Here are two nodes, and then these are the different types of waves that can happen between these two nodes. This one, what is the wavelength? Well, in a normal transverse wave, that would be what one wavelength looks like. So this is half a wavelength. Now see if you can get the rest on your own. The second picture is one wavelength, and the third picture is 3 halves of the wavelengths. How fast do waves travel? Well, we know the equation, speed equals distance over time. So in this case, since we're using waves, the distance is the wavelength and the time is the period. So, if the distance is the wavelength and the time is the period, and speed equals distance over time, then the velocity of the wave is wavelength over period, which also can be turned into wavelength times the frequency. If a wave with a wavelength of 12 meters is traveling at 6 meters per second, what is the period? So we're writing down our givens, which is 12 meters as the wavelength and 6 meters per second as the velocity. Velocity can be written as lambda times f, or lambda over period, which can be rearranged for period equals lambda over v. So plugging in our values, we get a period of 2 seconds. Now what about wave reflections? Here we have a wave traveling towards the wall on the top side. So when it hits the wall and reflects back, it's going to come back on the bottom because this is a fixed end. This only happens when there is a fixed end. Lambda remains constant, velocity remains constant, and period remains constant. The only thing that changes is that it's upside down. If it was not a fixed end, the wave would have come back again on the top. Now what about if two waves hit each other? Let's say two waves are coming towards each other with an amplitude of x. Once they come into contact, their amplitude then combines and becomes 2x. But what happens after they collide? Do they either bounce together and then go back the direction that they came, or do they go through each other? If you guessed that they continue the same way, you are correct. Now I hope you are able to answer the question, what are waves?